Between you and me, let's see who can pick the fastest moving thing. Well, what do you choose? Cheetah? Bugatti Veyron? Sorry, but you are out of luck because I choose RXJ08224300. This baby is a star that travels 5.4 million km per hour. It is also known as the Cosmic Cannonball. Are you impressed? I know I'm being unfair, picking something that few people knew. How about this? Round 2. Let's see who can pick the fastest thing that really near us. I pick Earth. That's right. Earth is orbiting the Sun with the speed of 30 km per second. It's just a little bit faster than your car. Now imagine, in 1 minute, the Earth is going to race Cosmic Cannonball in a straight line forward race. And we Earthlings want to accelerate Earth to the same speed as Cosmic Cannonball before the race. How fast do we need to accelerate the Earth? First of all, let me introduce some tools to help you to finish the job. We all know that acceleration means how fast something speeds up in a second. Hence, the formula A equals to V minus U over T. Just to be sure that you know, A is the notation for acceleration, V is for final velocity, and U is for initial velocity, and T, of course, for time. We can also play around with the formula and get a few definitions out of it. For example, if we configure it to explain the final velocity, we get that final velocity is initial velocity plus acceleration multiplies by duration of acceleration. Or we can configure it to explain time. It will be how many seconds you need is how much velocity difference you want divided by how many difference you make per second. In these particular problems, I will just simply use A equals to V minus U over T, since all I want to do is to find the acceleration. So now that we have the formula in arsenal, let's list down our assets. Now our object of interest is the Earth. We want to accelerate it to the velocity of Cosmic Cannonball. So all of the value that was listed should be of the Earth's. Initial velocity of Earth is 30 km per second forward. Do you notice how I include the direction in this velocity? It is because the velocity is a vector quantity, and to fully describe it, we need to have both magnitude and direction. Is it important in this case? Hell no! I just don't want to have someone complaining that I didn't do things by the book. And to play by the book, let's use SI unit for our calculation. Now this is important. Let's convert 30 km per second into meter per second, which we will get 30,000 meter per second. Now the final velocity, the velocity that you want Earth to have, is the speed of Cosmic Cannonball, which is 5.4 million km per hour, forward of course. To convert kilometer per hours, we multiply 1000 to convert kilometers to meters, and divide 60 to convert hours to minutes, and divide another 60 to convert minutes to seconds, like this. And we will get 1.5 million meters per second, forwards of course. Now, the time we have to accelerate the Earth is 1 minute, means 60 seconds. Now let's do the magic. A equals to V minus U divided by T. Substituting the values, and the answer is 24,500 meter per second square. And the direction of the acceleration is not towards left, not towards right, but forward of course. Well, this speed of acceleration is really intense. It's too intense. Earth's gravity is only 9.8 meters per second square. The speed of acceleration that you calculated is 25,000 times the gravitational force of Earth. What will happen? Perhaps perhaps the people on one side of the Earth will be flattened by the force, while the others will be swung away from Earth. And if Earth are still orbiting the Sun in that speed, maybe 1 year would mean 20 minutes now? Or maybe Earth will simply disintegrate? I'm neither a physicist nor astronomist, but my guess is we all will die. To prevent the distortion of the Earth, let's postpone the race for a while longer and accelerate Earth in a slower rate. Let's say half a G means 5 meters per second square. I wonder how long it will take. Now this time, we are trying to find time. V and U is still the same as previous question, and A acceleration equals to 5 meters per second square now. Now let's configure the formula to find T. Simple. Just switch the place of A and T like this. Substitute the value and we will get the answer. Tada! Looks like it will take 294,000 seconds, meaning 4,900 minutes, or 81 hours, or 3.5 days. It's actually a lot faster than I expected. But I think we all will still die if the Earth is moving that fast. So let's just cancel the race. Peace.